Okay, good evening, geometry students. These are the notes for Tuesday, September the 24th. I appreciate you finding time to look at your notes. Tonight we're going to discuss yet another topic that you have already spent some time in the past looking at, and that topic is going to be slope. Okay, our objective for today is the student will discover the process and applications of the slope formula. Again, these notes are for Tuesday, September the 24th. And pause the video anytime you need more time to write something down, and press play when you're ready to move on. Okay, now slope is typically thought of in the slope-intercept form. Of course, slope-intercept form is y equals mx plus b. Y and x are part of the equation, but m and b are constants that fit into the equation, and they give the line information about what it is that it's supposed to be doing. Okay? Now, a line needs two things to do what it does. Okay, first off, we need somewhere to begin in the graph, some point of reference that we can start from there and then move away from there accordingly. And the second thing it needs is somewhere to go from that point. Okay, now somewhere to start, okay, that point of reference, that's what we refer to as the y-intercept. That is the b part of y equals mx plus b. And the line, as we said, will also need somewhere to go. Okay, as we leave the y-intercept, we need to know what direction to go, how fast to go there. That is provided by the slope of the line, which is the m from y equals mx plus b. Another way of thinking about this is the slope is the coefficient of the independent variable, which is x, and b is the constant, just a number. It's not attached to the variable. It's just plus or minus some number. Today, we're going to be having a look at slope. Okay, the slope tells the line in what direction and how fast to move as it leaves the y-axis. Okay, now first off, there's many ways that a question can ask you for the slope value of a line. Okay, so unfortunately, we have a lot of different synonyms, and it does not matter how good you are at calculating slope or how much you understand the idea of slope. The fact is, if you don't recognize the question that they are asking, then you may not even know that slope is what they are after. So we do have to know all of the different synonyms just in case the question does not pick on the word slope. Okay. Well, first off, and this is probably a little unexpected, they could actually just come out and say slope. Find the slope of the following line. Okay, that's not very realistic considering all the synonyms that they have. In junior high, they may have asked us to find slope, but you can bet probably on a high school level test or ACT, they're going to pick on something more complicated, a more advanced type of a term. Okay. It is possible that the question could come out and ask for m. Okay. In algebraic terms, m is the variable for slope. Now, don't get that confused with a little m on a geometry type of problem, because a little m in geometry stands for measurement. Okay, so m for a graph or an equation is slope. M for a geometric drawing is a measurement. Okay. Here's another one that is probably a little bit unrealistic for us to hope that they could ask, is they could use the old junior high definition or explanation, rise over run. Okay. Again, they're probably not going to pick on that because they know that we understand rise over run. We've heard it put this way by our teachers for years, so probably not going to hear it termed this way either. Okay. What they could do is they could ask for the difference of the y values over the difference of the x values. This is not exactly a sneaky way of going about it, but you don't see it termed this way very often, which is one of the reasons why I think we need to know it. Okay, this is the formula. This is actually how the slope value is calculated based upon 2 points on the line. And we're going to be spending the good chunk of the math of this lesson looking at this fact, okay, looking deeper into what question number 4 actually says here. Okay. One of the newer languages that we run into is the change in y over the change in x, okay, written in that language. Now, if you read this, look and compare this back to question point number 4. What does number 4 actually say? The difference of the y's in the numerator. That measures the change in y value as you go from one point to the other. And then you put that over the denominator, the difference of the x values, the change as you move from one point to the other on the x-axis. These say, number 4 and number 5, say the exact same thing. One of them is in formula format, and 5 is in verbal format. Okay, they say the exact same thing, but they certainly do sound and look different when you see them. So we got to pay close attention. Okay, this is the more mathematical way of expressing it. What you see there is what is pronounced delta y over delta x. Now, if you haven't gotten to it yet, what you're going to start to see in your science classes and your math classes as well is you're going to see an emergence of the Greek alphabet starting to show up in your equations and your calculations and your formula. Delta is the lowercase Greek one of the lowercase Greek letters, and in the Greek alphabet, these different letters from the Greek alphabet are assigned certain meanings. Whenever you see this little triangle guy, delta, its assignment is change in. So in science, you're going to spend some time in the lab measuring delta T, and that is typically a change in temperature as you are doing an experiment. Okay. And the current term that seems to be the favorite these days, the test writers are picking on it quite a bit. It is possible that they would use the term rate of change. Okay, and they like this one because it does apply to a lot of different things, both mathematical and scientific. Okay, but when you see the terms rate of change, it is measuring as you move from one point in a situation to the next point in the same situation. What is the slope of the lines connecting them? Rate of change. That's kind of the flavor of the month, if you want to put it that way. And of course, all of these things ask for exactly the same thing. That is the slope value. So we need to make sure that we're familiar with all of them, just in case they happen to ask it any of these different ways. We know what they're talking about. All right, now slope is a fraction, whether it is written as a fraction or not. And a lot can be determined about a graph, an upcoming graph, just from observing the slope value in the equation of a line. Okay, so we're going to look at several different characteristics and qualities that slope might show you. Okay, so if your slope value is positive, okay, that's a possibility. We'll have a positive slope. What that tells us is that the line will move upward as you look from left to right in the graph. And that is how we read graphs, from left to right. Okay, from left to right, this graph is climbing. That means it has a positive slope value. The flip side of that will be if a slope value is a negative number, then that means the line will move downward as you read from left to right in the graph. Okay, if our slope value happens to be a value larger than 1, okay, value larger than 1, what that will mean is if you think about rise over run, that will mean that it is rising faster than it is running. A bigger rise, a smaller run. That will cause the graphs to move upward or downward very quickly. And the flip side of that condition is that a smaller value, or a value smaller than 1, that will mean that it is running faster than it is rising. Okay, that means a small rise and a large run. That's going to cause your line to move upward or downward more slowly. Okay, a couple of special cases If your slope value is such that the line runs but refuses to rise, that means that the line has zero slope and the line will be horizontal. Now, a little side note on here, there used to be some acceptable language, so you may have had a teacher that told you that no slope was an acceptable way of describing the line that you're looking at right there. Here in the last few years, the powers that be have decided that no slope is not a good term to use. So if you did learn no slope, we're going to need to get that one out of your vocabulary. The correct way to describe this one is zero slope. Okay, and if your slope is such that a line rises but refuses to run, then the line has what we refer to as undefined slope, and that line will end up being vertical. Okay, so responding to a question about the slope of a vertical line, you may say the term undefined. You may also say the term or use the symbol for infinity. Okay, so we're going to do the same thing now that we've done the last couple of days. We're going to look at one guided example of a calculating slope based upon a couple of coordinates, and then I will give you a couple of additional problems to copy down. And if you feel confident on your calculations from what you see on the first example, you may go ahead and work the two additional examples, and we will run back over them very quickly in class so you can see if you got them right. The first example is, what is the slope of the line connecting points -2, 3 and 6, 7? Well, just like any of these other equations that we've been working on that have these 2 points, our first step is going to be to label our points x1, y1, and x2, y2. And just like with the other days, remember that each point has an x and a y, not two x's or two y's. Okay, and our second step, just like it was with distance and midpoint, is going to be, we have a formula. Anytime we have a formula, we're going to write that formula down before we decide to start plugging things in. So after you have your points labeled x1, y1, and your x2, y2, and your formula written down, now it should be a lock that we can plug our points into the formula exactly the way the formula calls for it. So in the numerator of the formula, it asks for y2. That's going to be a 7. y1, that's going to be a 3. Okay, and notice that the formula has minus signs built into it. It's going to be subtraction. And in the denominator, x2 is going to be 6, and x1 is going to be -2. Pay close attention to your signs. We're going to get some double negatives and things like that going on. And again, pay attention to the fact that the formula has minus signs built in. So when we plug our numbers in, this is what it should look like. We should have 100% accuracy getting to this point. Now we just need to deal with the math. Okay, so what's the numerator of this fraction going to look like? 7 minus 3. Everybody should be able to get that one. That one's going to be 4. What about the denominator? 6 minus -2. Okay, well, in the denominator, you can see you've got the back-to-back minus and negative signs. You remember what happens when you see this? The two negatives join together, they become a positive. So another way of reading that is to say 6 plus 2, and 6 plus 2 is obviously 8. Okay, so we expect our slope to be a fraction, so we can see a fraction starting to develop here. The only thing we need to do is check and see if this might reduce. Will anything go into a 4 and an 8 at the same time? Obviously a 4 will, so 4 over 8 will reduce to 1/2. Okay, so if the slope of this line connecting these 2 points is 1/2, what is it that we know about this line? How will this line act in a graph? Well, a couple of things we can tell about this line. First off, our slope value is positive. What is this going to mean to the graph of the line? Positive slope. Well, positive slope is going to mean that the graph is going to rise up as we move from left to right in the graph. How about the fact that it is a number that is smaller than the value 1? 1/2 is smaller than 1. What's that going to make the line do? While it's rising up as you read from left to right, it is not going to rise particularly fast. It's going to rise more slowly. Up 1 over 2, up 1 over 2. Okay, here's the second example I'd like you to copy down and give it a try in your notes there. What is the slope of the line connecting points -4, 7 and 0, -5? Press pause, copy it, give it a try, and then hit play again for the final example. And the final example is, what is the slope of the line connecting points 3, 2 and 3, -1? Give that one a try as well. We will run through those last two in class first thing on Tuesday. I appreciate you finding time to do your notes. Hope you have a good Monday evening.